Hi everyone. So today we're going to talk about motion. Right? So we're going to take a first look at motion. So this is in our unit of kinematics. Before we even start, I want you to pause this video and draw a diagram of a car coming to a stop. Right? So once you're done with that, you can just hit play again. I know we haven't talked about this in class yet, but I just want to see where you're at on how to diagram a certain situation. So there are different types of motion. So first let's talk about what motion is. So motion can be defined as the change of an object's position or orientation with time. All right. We can also right now define trajectory. And a trajectory is the path along which an object moves. Right? So a trajectory can be a straight line or it could be curved. Right? Generally when we think of a trajectory, we think of something flying through the air. Flying in quotes. Well, this is the trajectory. It's the object's path of movement. There are four basic types of motion. These can actually be argued by other physicists and other textbooks. But right now I'll just say that we can think of them as there's straight line motion, there's circular motion, projectile motion, rotational motion. So we'll actually talk about all of these types of motion in this class. But for the time being, for the next few lectures, we're just going to talk about straight line motion. So as you can imagine, that's just motion along a straight line. You know, difficult vocab. All right, so the rest of this lecture is going to be focused on diagramming motion. So we're going to talk about motion diagram. So what is a motion diagram? This is a composite image showing an object's position at several equally spaced instants of time. Excuse me, I'm having trouble speaking today. So imagine we saw a car driving along a street and you took a picture of the car at regular time intervals, let's say every second. So as the car passes you in the street and you take a picture of the car every second, you'll see an image something like we have here on the left, where we see a car basically moving across our plane of view. If we composite this image, so superimpose the image or put these images on top of each other, we can see we'll get an image something like here on the right, where we see the car at equally spaced points along our path. The reason why it's equally spaced is because the car is moving at the same speed, and we'll talk about that a little bit more in a moment. But the important part here is that the same amount of time is elapsed between each image and the next, right? And that's the motion. That's an important part about the motion diagram, because we can analyze the object's motion and speed based on that information. Right. So if we see up here on the top left, we have a skateboarder who has equal spaces in between these moments in time, if you want to call them. So because the images are equally spaced, that's indicative that the object is moving at a constant speed. So the skateboarder here is moving at a constant speed. To the right here, we have someone on track speeding up, and we see that they're between these, let's say we took a picture every 1 second, between these 1 second intervals, the space in between them gets bigger. That's indicative of the object speeding up. On the bottom left, we have a car slowing down, so the spaces in between the images decreases, and that shows an object slowing down. We can also have more complex motion diagrams, and that shows change in speed and direction. So we see here a basketball moving in 2 dimensions here. And we'll talk about better ways to diagram motion. And this is just a basic overview of one way to diagram motion. So I want you to pause the video to stop and think. So looking at these two diagrams of car A and car B, so the red car and the yellow car, based on what we've just learned, or what you hopefully have learned, which car is going faster, car A or car B? Assume that there's equal time intervals between the frames of both videos or both motion diagrams. So take a pause, come up with an answer, write it down, and then we'll talk about which answer is correct. All right, welcome back. Hopefully you paused the video. So we see here the car on the left, the car A, has very small distance between each time interval, whereas car B has a larger distance between each time interval. So the time intervals are the same. The car that travels a further distance in that amount of time is going to be going faster. So car B is going faster. Hopefully you got that right. If not, rewind the video, take a look at the description of motion diagrams again, and hopefully you'll understand. If not, ask me in class. Now, I'm pretty lazy when it comes to drawing motion diagrams. Physicists are in general. Drawing out, say back here, a car every single time is going to take a lot of time. This is why physicists and you, in theory, will be implementing the particle model. Right? So this is just a simplification to consider an object as if all of its mass were at a single point without any size and shape. So this is what we're doing here is called making an object a particle. So a particle is an object that can be represented as mass at a single point in space. So we're going to assume or model any object we're dealing with, at least for the time being, as a point particle. Models allow us to focus on important aspects of the phenomena or the problem we're looking at by excluding details that play a minor role, right? So actually in this case, assuming all the mass of an object being at one point is actually a major role, but it just makes the analyzing that motion much more complicated, not an AP1 level problem. So we're just going to assume that everything's a point particle, or that we can make that assumption. So just to remind you, we're just assuming everything is, all of its mass were concentrated at a single point, and that's actually going to be called the center of mass. But we'll talk about not dealing with objects in a particle model sense when we deal with rotational motion in a number of weeks. So how do we change what we're looking at from the motion diagrams to a particle motion diagram? You can use that term. So if we look here up top, we have a car that's slowing down. We just basically, instead of drawing a car, just put a dot. Makes life a whole lot easier. So we'll assume all of the mass of the car is concentrated at one point. And then now we see we can simplify this, this diagram to just dots that are going from a larger space apart just to smaller places in between to show that it's slowing down. Remember, it's still the same amount of time elapsed between each frame, so each dot. If you want, you can number your dots to show the number of frame. That way it's easy to analyze whether an object's moving from the left to the right or right to the left, up, down, up. Numbering your dots helps that. You can also draw arrows on your dots. That's what I like to do. Basically, that's actually going to tie into something called vectors. We'll learn about it in a couple days. Basically, these velocity vectors or speed arrows show us what direction the object's going. This diagram here to the right just shows how you can also diagram objects going up and down. So here we have a diver who's jumping off, or actually we don't know if they're jumping off. They're falling as far as we know, but they're falling down to hopefully some water. And we can represent this diver as just a dot. And here they have numbered the dots to show that this diver is falling downwards. Now, time again to pause the video in just a moment. So here we have three different motion diagrams, A, B, and C. Identify which of these diagrams is a dust particle settling to the floor at a constant speed, which diagram is a ball dropped from the roof of a building, and which is a descending rocket slowing down to make a soft landing on Mars. So pause the video and then we'll talk about the answer. All right, so let's analyze the dust particle first. The problem says that the dust falls at a constant speed. So it's moving at a constant speed. We're going to have equally spaced time intervals and equally So we cover the same amount of distance in the same amount of time. So it's not going faster or slower, it's traveling at the same speed. So that's going to be option B, right? The dots there are equally spaced, so it's moving at a constant speed. Next, a ball being dropped from the roof of a building. When you drop a ball, gravity actually causes the ball to accelerate. So we'll start off slow and get faster and faster. Right? You've seen that every day in your life, actually, even without noticing it. But so we have, if you drop a ball through a building, we'll start slow, get faster. So that means smaller spaces will get bigger and bigger. So that's going to be option A. And then finally, good testing strategy. We've already gotten rid of A and B, so we know C is going to be the rocket slowing down, but we can also come up with the answer by analyzing the situation. So we have a rocket slowing down, so we're going to have larger spaces becoming smaller, so that's going to be option C. So that's basically what I have for you today. Homework. There is homework on this lesson. It is linked to the Google Doc. It's lesson 1, the motion diagrams, and you can find that link to the Google Doc on Blackboard. Now would be a good time to look at your diagram that you have made at the beginning of this lesson, when the do now. What do you think of it? Do you need to add things to that motion diagram? Do you need to take things away? Can you simplify it? Does it need to be more detailed? Use your best judgment. All right. Thanks for listening.